That's it. I just need to put that on. Let me see.
Then you can walk around.
But I'm still finding an issue here that I've not seen before is when I go like this, it doesn't give me the slide that I want to see up here. I haven't seen that happen before. No, I see that. I see that. It's just that I normally see it here as part of my... Okay, I think I'm good. I'm good.
Did you find it?
Yeah, it's something that PowerPoint does that it does on its own initiative. So it's already a good turnout.
It is a good turnout. I'm impressed. You know what's good?
Yeah, people have fresh.
There aren't that many things that are competing with it.
is. Just tap it, see if it works.
Okay. Morning, everyone. We're going to be starting in just a minute or two, so I'd like to invite you to take your seats and come down as close as possible. Thank you. All right, we're going to get underway. Thanks so much for coming. It's great to see such a nice crowd this morning. I think that the weather made me a little bit nervous. I think as the day goes on, no one's going to want to be inside. So good morning again. My name is Patsy Fisher, and I'm Director of Class Activities at Dartmouth College Alumni Relations. And I'm so happy to welcome you back for your reunion, and really delighted that we can have such gorgeous weather on tap for you this weekend. This morning's program, Engineering and Medicine, Partners in Innovation, is one of the Alumni College at Dartmouth events during our June 2012 alumni reunion, and it was coordinated jointly by my professional school alumni relations colleagues from the Thayer School of Engineering and the Geisel School of Medicine at Dartmouth. On the Thayer School website is an excellent article on engineering and medicine, and the first two lines read, "Behind every great medical advance, there's a great engineer. Anyone who goes to the doctor benefits from the work of engineers." Unquote. Collaboration between engineers and medical professionals has been going on at Dartmouth for decades, both in the classroom and in the laboratory. Current day research collaborations include Dartmouth's Biomedical Engineering Center for Orthopedics, the Center of Cancer Nanotechnology Excellence, the Advanced Imaging Center, and the upcoming Advanced Surgery Center for Translational Research. Our two speakers this morning will describe two areas of innovation driven by the application of engineering in medicine. Briefly, I'd like to introduce both of our speakers, Alex Hartoff and Eric Coble. Alex Hartoff, Professor of Engineering, received the BSEE degree in Electrical Engineering with high honors from Northeastern University and the Master of Science and PhD degrees in Biomedical Engineering from Dartmouth's Thayer School of Engineering. He joined the Thayer School faculty in 1996. Dr. Hartoff directs both the master's and doctoral programs in engineering. Among the courses he teaches are a course in digital imaging processing, a seminar of science, technology, and society, and one of applied science and technology, as well as overseeing the professional workshops for doctoral students and their research in Progress seminars. Dr. Hartoff's own research interests center upon medical imaging. His projects have been in the areas such as electrical impedance imaging, EII, for breast cancer screening, EII for prostate cancer screening, image-guided neurosurgery, fluorescence-guided neurosurgery, and automated segmentation. He's going to explain what all that means. Dr. Hartoff's talk today, Prostate Cancer Screening with Electrical Impedance Imaging, will give an overview of a project in which EII was evaluated for its ability to detect prostate cancer. Our second speaker, Eric Coble, is Assistant Professor of Neurology at the Geisel School of Medicine at Dartmouth and Adjunct Assistant Professor at the Thayer School of Engineering. He received a Bachelor of Science in Chemical Engineering from Columbia University, earned his PhD in Biomedical Engineering here at Thayer, and completed his medical degree here at Dartmouth Medical School in 1991. Following medical school, he did a residency in neurology and fellowship in neuro-ophthalmology at the Walter Reed Army Medical Center. Now, as a specialist in those fields, his clinical and research interests are clinical neurophysiology and epilepsy. He has published on a broad range of topics, but mostly focusing on the quantitative analyses of neurophysiologic signals from patients with epilepsy and brain injuries. Dr. Coble serves as a course director for the Neurology Residency and Clinical Neurophysiology Fellowship programs, as well as the Neurology Grand Rounds Lecture Series at the Dartmouth Hitchcock Medical Center. He has established weekly lecture series curricula for clinical trainees and students both in neuro-ophthalmology and clinical neurophysiology. In addition, he has implemented an epilepsy clinical neurophysiology elective for Dartmouth medical students, as well as a clinical neurology shadowing program for Dartmouth College undergrads. At Thayer, Dr. Coble teaches in the Biomedical Engineering and Quantitative Physiology courses and collaborated with colleagues on a number of medical devices and pharmaceutical industry-sponsored clinical trials. In his talk today, Biomedical Engineering Applications in Clinical Neurophysiology, he will discuss how the field of study involving technology, biology, and medicine has led to techniques and new approaches to diagnose and clinical treatment today. After Dr. Hartoff and Dr. Coble speak, I'll moderate a question and answer session, and I also want to note that this lecture is being recorded and will be available on YouTube in the very near future. Please join me in welcoming Alan Hartoff and Eric Coble. Thank you.
I think this works now. Can you hear me? Okay. Thank you for a very kind introduction. And let me start by prefacing my talk by emphasizing that this is not just my work, it's the work of a lot of people, some of whom are here at Thayer School, in fact, some of whom are sitting here in the room, and some of whom are at the medical school, including Dr. Heaney over there. And this is a collection of slides that I picked from various presentations that either I or my students gave over time. And my purpose here is not to make you experts in prostate cancer screening, but rather to give you an idea of the kind of work we do here at Thayer School in collaboration with the medical school. And so you could go home and understand a little more what we're doing here. The project that I will be speaking about proposes to image using a technology that is not widely used for medical imaging, which is simply to apply small currents on a patient's skin or other parts and measuring the resulting potentials, and from accumulated data from many electrodes, try to reconstruct the electrical properties inside the body, or at least within the vicinity of the electrodes, and from that, knowing that there is a correlation between those electrical properties and the condition of the tissues that you are imaging in this fashion, be able to diagnose various conditions. In our case, we have looked at breast cancer, and we have looked also at prostate cancer. Other people have looked at other parts of the bodies and other goals for doing that. But today I will speak of our attempt at imaging the prostate using electrical impedance imaging and determine whether or not it would be feasible to use that as a diagnostic method for prostate cancer. Okay? So, to start, I will give you sort of a rationale for what we're doing and begin by the most basics, which is what do we mean by bioimpedance. Impedance, generally speaking, is the property of a material or an object to let current flow, and it has two components, one of which is the resistivity, or its inverse, the conductivity, which is its ability to impede current flow directly, and another property which is its permittivity, or in by comparison capacitance, which is the ability of a material or an object to hold charge. Okay, so those are the two properties we are looking at, and these properties, when we're talking about tissues, are affected by ionic concentration in the fluids that make up the tissue, interstitial fluid inside the cells, the integrity of cell membranes, morphological feature of the cells, how big they are, how compacted they are, the cell types, the tissue types, whether or not there is flow, and whether or not there is a temperature change. So basically, imagine that we are looking at a chunk of tissue. We put an electrode on both ends. We apply a current to that tissue through a current source, and then we measure the voltages. The ratio that we get of current to voltage is what our impedance is. And that ratio encompasses those two properties of conductivity and permittivity. Okay, so it's a fairly simple conceptual device. But it gets complicated because what we are measuring is not homogeneous. It's a very complicated thing, and it's made largely of cells, and these cells have a membrane around them. That membrane does not let ions flow freely from the inside to the outside. That's its major function, is to isolate the inside from the outside. And therefore, when we apply a field, electric field, to tissue, what we are looking at is how the current travels through the tissue in the form of ionic flow. The electric field that we apply makes the ions want to move in a direction, and the overall effect that we see as current encompasses the action of many such cells. There are approximately 50 to 100 million cells to a centimeter cube, so it's a lot of cells effect that we measure. We cannot measure the individual effect of a cell, but we can certainly see the bulk effect it has on how current travels through the tissues. At low frequency, since the membranes are impermeable to ionic flow, we basically sense through impedance how the current can travel around the cells in what is known as the interstitial fluid. That is one characterization of the tissue that we can collect. At much higher frequencies, if you imagine the ions flowing under the influence of an alternating field, they basically go back and forth. And as your frequency is much faster, they go back and forth over a much smaller distance, which means that they no longer accumulate across the membrane, which is polarization, and they can, in effect, give us an effect that includes the path through the membranes and inside the cells. So we can, in effect, due to this higher frequency sense, in terms of the electrical properties, of course, what is happening inside the cell. So you can see that overall, we are able to sense at lower frequencies what happens around the cells, and at higher frequencies have the added effect of sensing what is happening inside the cells. Another way to think about that, if you are familiar with Maxwell's equations, is to think in terms of displacement currents, but that is not necessary to get an intuitive understanding of what goes on when we apply a current to a patient and why it is that we can recover certain properties. As I said earlier, we're not looking really at the effect of a single cell, but rather we're looking at the effect of many cells. And globally, the bulk property of the tissue we can usually summarize by making measurements over a number of frequencies. And it has these general properties that as you increase frequency, conductivity goes up. And that has to do with the fact that we are measuring ionic flow outside of the cells. And in addition to that, the flow inside the cells becomes a component that has some effect. And permittivity tends to peak at a certain frequency and drop off at both high and low end. And we can combine these two properties in a figure such as this, which represents the behavior of the impedance if you plot the permittivity versus the conductivity, or if you're familiar with a complex plane, that is a complex plane representation of these same properties. The reason I bring that up is that we can, from this type of semicircular plot, extract specific parameters, which are illustrated here, one of which we call the characteristic frequency here, another one which we call the low frequency conductivity and the high frequency conductivity, as well as an alpha parameter that essentially gives us the center of that circle in the complex plane, and the distance between the extreme here, which is the delta sigma, or the conductivity range. So the idea here is that we can make measurements over many frequencies and summarize the properties of the tissues with a few parameters that to us have some value in characterizing the condition of the tissue. The idea of using bioimpedance for cancer screening has been tried in a number of areas. I'm familiar with one in breast cancer, which was a big project here and still is a project here. Some people have tried it to detect bladder cancer, cervical cancer. There is a group in Britain that has been very successful in building a device to screen women very inexpensively and very effectively. And also for skin cancer. So this is just one of the many applications that we decided to try. Let me give you a rationale for why we did the project that we did. About 6 years ago, Ryan, who at the time was my student, and I went in the OR, and Dr. Heaney let us bring in the OR a cart full of equipment, and handed us prostate shortly after it was excised from a patient, and showed us where the prostate cancer was located, and we could measure with a custom probe the impedance in that particular spot, and also measure elsewhere what the impedance were, so that we had a built-in contralateral, if you will, or control point. And we did an analysis of the data, and it showed very clearly that there is a significant statistical difference in the conductivity over the frequency range, and that one, in principle, should be able to discriminate between normal and cancerous tissue. This, of course, is not the way you would want to do the diagnostic. It's not very amenable to widespread use. But the idea was that we have a rationale for attempting to measure these properties without removing the prostate, and that's what led us to submit a proposal which was funded to image non-invasively those prostates and see if we could establish whether or not there was a cancer. This is further evidence that we can distinguish between cancer and normal tissue. I won't dwell on that except to say that this FC, which is one of the parameters that we extract from the spectral data, impedance data, is apparently quite a good test for detecting whether or not we have a cancer. The area under this curve represents the suitability of a given test for detecting a condition that you establish. Basically, if you were along this diagonal line, your test is no better than chance, 50-50, whereas if your curve covers the entire area here, which would be 100% area under the curve, it's a perfect test. It's right every time, never has a false positive or never has a false negative. So this is a way of establishing the value of a diagnostic test, and the characteristic frequency appears to be quite a good test. But of course, this is based on contact data, so we need to validate that using non-invasive method, which is tall order. The further rationale that we hypothesize for why it is that impedance is able to discriminate between various tissue types simply has to do with the morphology of the tissue as seen under a microscope. Normal stroma in a prostate has this appearance and is very conductive. Functional units in normal glandular tissue have, I didn't mean to do that, have these openings which are non-conductive, so the conductivity is slightly smaller, there being more obstacle to the ionic flow. And as you have more of these openings in the tissue, which is a feature of benign prostatic hyperplasia, your conductivity further decreases. And when you have cancer, in addition to a large number of openings, you have a highly disorganized a structure to these lumens, and it's even further reducing conductivity. And these are slides that we collected from the same patients that we imaged in our original study. So here comes the imaging part. We devised first we found out that a company was producing a 3D imaging system for prostate examinations. When we saw that, we decided to purchase one of those and adapt it for impedance imaging so that you can see now we have two imaging modalities coupled, and that will be a key element of our system, as you will see in a moment. Suffice it to say that this device is able to produce a three-dimensional imaging stack that covers the entire prostate, and that we use that information, that is the shape of the prostate and its position with respect to the probe, to guide the reconstruction of the electrical properties that we need to render a diagnostic. These are electrodes. The copper-colored part here are electrodes. This is an opening that fits over the acoustic window of this probe, and then there are traces that go back to a connector here that attaches to our impedance tomography device, which basically is a source of is a current source that can be switched to any number of electrodes, and the voltage sensing is going to an analog to digital converter, and all the data is collected automatically with a computer. Let me see. This here is the same electrode array, but now mounted on the imaging probe, and you can see that we have 30 electrodes around the acoustic window. And further view, this is a view of the same device with a biopsy needle probe. Not an enjoyable sight for some people. In any case, our device operates in the range of 400 hertz to 100 kilohertz. And we take, I believe it's 5 frequencies in that range. Yu-Ching, can you remind me?
4 frequencies for the patient data protection.
Okay, 4.
And it works at 9 frequencies.
Okay. And this is just to summarize the system. We have an imaging guide that has electrodes that connect to a data acquisition system, and the entire process is automated. And this is a detail of how we apply currents. Current needs to have two electrodes, one to go in, one to go out. We apply the current, which generates a electric field in the tissue in the vicinity of the electrodes. The other electrodes, which are depicted in blue here, are used simply to sense the potential at those points. The round electrode that you see there is to remind us that there is one additional electrode that we apply on the abdomen of the patient for collecting data. And so what we do is that we switch the electrode pairs that drive the current, and for every electrode pair that drives the current, we measure the potential on all the others. And that information combined allows us, through a fairly complicated mathematical process, to reconstruct the tissue properties within a volume nearby the electrodes. And this is the scene in the OR. Resident there inserted the imaging probe in its location, and you can't really see what's on screen here, but if you could, you would see a cross-section of that gentleman's prostate, and once it's positioned properly, then we acquire a 3D stack of images in ultrasound, and at the same time we acquire the impedance data. Through some magic that has to do with Maxwell's equation, we are able to reconstruct, and I'll skip that part if you don't mind, to reconstruct in a numerical model our electrical properties. Okay, so the process involves modeling the patient basically as this cylindrical tube with the imaging probe inserted in the middle of it, and a certain volume shown there representing the volume that we are able to image with the ultrasound, and within which we would like to reconstruct the properties, the electrical properties of the tissue. This is a detail of the numerical model that we use. And one important detail about that model is that it is actually patient-specific to some extent, in the sense that we use the data that we collect from the ultrasound to create a spatially co-registered model of the prostate of the patient within the model that we use for the computation. And that we have demonstrated convincingly does help significantly improve the quality of the images that we reconstruct, and that's an important detail. Here is an outline, if you will, of the steps involved. We first segment manually the prostate. Segmenting only simply means delineating a particular organ or feature that you're interested in those images. We create a surface mesh of that segmented prostate. We create a three-dimensional mesh, volumetric mesh of that prostate, which we then integrate into our numerical model of the patient. We stitch the prostate model within that volume, and that's what we use to reconstruct our tissue properties. There are find elements which we use to calculate the field properties, and some coarse elements which we use to compute the tissue properties, and that's necessitated for practical reasons having to do with not waiting 3 or 4 days to get a result, so we need to take some shortcuts. Let me see. These are some experiments that are numerical in nature, meaning that we tested our reconstruction, our ability to reconstruct some of our prostate model using numerical simulations. And basically what this shows is that if we were to use a mesh that does not incorporate the model of the prostate that we have difficulties, in this case, recreating the drop in conductivity, which could correspond to a tumor within the prostate, by not representing the prostate accurately and just letting the system compute the electrical property for every node in our finite element model. Whereas if we model the boundary of the prostate, its proper location and position with respect to the probe, we are in fact able to recover a significant dip in conductivity within that region, which we could not do before. So this is the evidence that we have that using a patient-specific model does improve the quality of the reconstructed images. This is further evidence to that effect, but this time instead of using numerical simulations, it is based on experimental data acquired by Yuqing, and he did the reconstructions. And we can see that there is a visible, a visible drop in the conductivity within this volume here, which is a piece of agar in which we have embedded a non-conductive plastic object, okay? This is the same experiment as this, but now looked at from a different perspective, with and without using the priors. Overall, what we are able to do then in the operating room is to overlay the original images of the prostate and the reconstructed tissue properties that we obtained from running the reconstruction. And presumably in the future, we would show that to the surgeon to see that perhaps he should take that prostate out, or maybe he should leave it in there. There's another issue that I haven't discussed so far, which is that while we may be able to find a cancer in a patient, we don't always know what to do with it, because some prostate cancers will not harm the patient for many years, and some are very aggressive and need to be taken care of promptly. So another directions in which this project has gone, and I won't talk more about this after this mention, is that we are hoping to be able to also tell whether or not a prostate cancer is aggressive or of a more benign nature that can be handled by simply monitoring the patient carefully. So the electrical properties of the tissues, in fact, we have some preliminary evidence that they could conceivably lead to this decision, which right now is a very difficult one for urologists. Okay, so we've shown that we can image an object, we can see what's inside it. Now we need to get some validation for what we're doing, and this was done in conjunction with the physicians at DHMC, particularly Dr. Alan Schned, a pathologist, where we did a study on, I think it was 66 patients total, in which we imaged patients immediately prior to resection of the prostate. We collected the ultrasound and the impedance data that I just spoke of. And then after that, those prostates went to the pathology department, were sliced, imaged, and the pathologist provided us with maps of where tumors were located. This particular part here is supposed to have the outline of circular cross-sections of tumor, but it doesn't show very well here, I regret to say. And from those maps, well, here you have a little better idea. These are the kind of images that we get from pathology. These are the prostate cross-sections that we have from our ultrasound imaging. So what we do is that we sort of morph those images into that shape so that we can co-locate those tumor locations onto our image, and from that get an idea of whether or not our imaging systems tells us something that makes sense in terms of what we know of the tumor location and presence, okay? This is another way to illustrate the same idea. We have some information at the microscopic level of the nature of the tissue. This particular slide corresponds to a cancer that here was outlined in a large cross-section of the prostate. As you can see, it has been diced to be looked at under a microscope and then reconstructed. And there you have the map that pathology gave us to conduct our validation study. And up there you have the corresponding impedance imaging cross-section that we recovered from that same patient, okay? And these here are a bunch of such images. If you think in terms of a stack of images going from top to bottom, we try to line up the 4 types of images that we have for a given patient, which are our operating room ultrasound images, the sliced prostate itself, the map that the folks in pathology give us, and the impedance tomography reconstruction corresponding to that slice. And we can visually assess how often we are matching what pathology told us. And we can also do a statistical analysis of those results and decide for ourselves how good we are in matching those results. And the results are that we are finding statistically significant differences. Now, I don't know if I'm exceeding my time here. Eric may not be able to talk. So what I'll do here, I'll show you the last slide. It's the most important of the talk. And that's not the one. All right, let me just jump to it. That's the one I wanted to show you. And leave it at that for now. Okay, so those are most of the folks involved. Some of them I didn't get the picture. So this is Yu Ching, Ryan, who's sitting up there right now. Dr. Heaney is here. Dr. Schneid and Dr. Sain are not here. Andrea here is the guy who developed much of the computational component of our system. Haider and Vaishali are 2 of our students who worked on the project, who are still students. Yu Ching worked this year and got his PhD, so I have to address him as doctor now. Thank you very much. Okay. The questions will come at the end, if you will. Yeah. Oh, sure. Sorry.
Can everyone hear me? Or okay. So a tough act to follow. I'll actually try my best to touch both on clinical applications as well as a few of the research projects that I'm involved with. I'm actually collaborating very closely with a number of the Thayer faculty now, which has been just a wonderful thing. I actually returned here about after having studied here during finishing in the early 90s, but then returned here less than 2 years ago. It was actually a great opportunity and kind of serendipitous in a way, and I just was very appreciative that along the way Dr. Sol Diamond actually called me up, having found out that I was here, from my former doctoral advisor, Andy Daubensbeck. And then it's been just fantastic. Things are taking off as far as the research possibilities that we have, which has been fantastic. I actually, during my medical school studies and also even while I was an engineering student, I basically fell in love with the brain. It was just, to me, the perfect engineering machine. And it's the rest of the nervous system is also can be thought of in the same way. But to me, the brain was the most complicated, yet the most interesting part of the body. To me, there was no question about it. And I just am very appreciative that since I've finished my studies, things are kind of taking off as far as the technology finally becoming realizable, as far as being able to apply the engineering methods, the computing techniques that we have, everything, computational, numerical methods, imaging. It's just really a fantastic time to be in the field of neurology and clinical neurophysiology. And I think we're at the cusp of really, really probing into the brain and really finding out a lot more of what the brain does, what it doesn't do so well when disease processes unfortunately afflict our patients. So it's just a fantastic, fantastic time to be in the field of neurophysiology and to have all of the engineering techniques to study the brain and other parts of the nervous system. So as far as just basics, what do we normally do with electrophysiologic recordings? Well, you're probably familiar with most of these things: electroencephalography, electromyography, nerve conductions. But one of the things that I actually, again, fell into while I was after my residency is that there's a new field that was emerging called Intra-Operative Neurophysiologic monitoring. And it seemed like a perfect fit for someone like me who has a technical background, in which you apply some of these techniques and other techniques that I'll talk about in the operative setting. So you're actually, to me, it was kind of where the rubber meets the road as far as how to apply clinical neurophysiology and get the most immediate and some of the most fulfilling benefits of the engineering techniques that we'll talk about. And then there's the field of functional neuroimaging, which I'm starting to become involved with, but it's a little bit beyond the scope of this talk. So we'll touch on these, and we'll also talk a little bit about some of the research that I'm doing. So, as far as clinical neurophysiology and technology, it was the first reported use that I could find was back in 1898. So it's quite a while ago, and one would think we would be far beyond where we are today, since more than a century has passed. As far as when you did your first electrical recordings in the body. There are a couple of things that held us back, and I think a lot of it is just the technology was not portable. The technology was hard to get. You couldn't do the computations online. The measurements are fraught with problems as far as signal processing issues, et cetera, et cetera. SSEP, actually, I apologize for the abbreviations, but it means somatosensory evoked potentials, were actually used during thalamotomies, which are it was a surgical procedure that was for patients who had medication refractory Parkinson disease. That was kind of used back in the mid-60s. And then people started recording EEGs during carotid endarterectomies. And that was actually useful because when you're actually occluding the carotid or mucking around with the carotid, you want to know if someone is having a stroke or any sort of ischemia to the brain. And the EEG can give you an index of what's happening during that part of the procedure. And then there was a lot of instrumentation for spinal cord procedures, as well as spinal cord tumor resections. And somatosensory evoked potentials were used in the early 70s. But then there was kind of a long hiatus between using clinical neurophysiology in the operative setting. And I think what really held it back was the portability and also the computational abilities just weren't quick enough. Surgeons are the type that want to know exactly what's happening at the time. They don't want to wait for your numbers to be crunched. Like Alex said, you don't want to have the numbers crunched for a day or two, and then they come back and, oh, I resected the wrong part of the prostate. And even more so for the brain when you're actually trying to resect a seizure focus, or you're trying to resect a brain tumor, et cetera, or trying to clip an aneurysm, what have you. So it's actually now widely practiced, and it has been since the mid to late 90s. And it has proven benefits. And the advancements in technology have been fully more realizable. So this is what we used to do. And you can imagine a neurosurgeon just looking at blips on this oscilloscope screen that we used to use for clinical neurophysiologic recordings. And then we had a huge advance. Chart recordings, okay? Again, fraught with real problems because pens run out of ink, pens get clogged up, you have a mess. I actually used some of this during my doctoral work when we were doing our recordings in the physiology lab. But finally, we entered the digital age, and that's really what kind of made this all take off. So things became digital, and this is what we used to have, big mainframe computers, which were digital, but they weren't portable. And then so now we have something like this, where you have a laptop where you have signals going across the screen. You're in your little corner in the room, away from people. The scrub nurse is not yelling at you because you have this monster of a machine in here, with the mainframe computer. So, and plus, not to mention, you get everything online. You can do your recordings. You can look at things. You can multitask. It's really fascinating. And I actually am able, because of engineering technology, able to actually see what's happening on the screen from the comfort of my own office, actually. So it's good. I can have the tech in there. Before, the neurophysiologist would have to be physically in the OR. So this actually enables me to be able to do other things. I'm not a very highly trained technologist. So I can, engineering has really facilitated a lot of things. So the primary goals of intraoperative monitoring specifically, and clinical neurophysiology in general, and I kind of use IOM as kind of an example because it's one of the newest components or newest subspecialties within neurophysiology. So what you're trying to do is preserve the nervous system during surgery. So you actually will have, because patients have baseline pathology, you will actually have maybe some abnormal signals to begin with, but at least you can see online within the OR signals changing as people are doing things like retracting, things like clipping aneurysms, things like resecting tumors, instrumenting the spine. So you can see things happening as they are occurring. And this gives the surgeon a warning that what they're doing could end up really wreaking havoc on the nervous system. So that's a really important thing, and it's just really a fascinating application. And there are a lot of studies out there to show that it does improve patient outcome, and there's facial nerve preservation when you're doing things like acoustic neuroma resections in the back part of the brain. You're pressing on that facial nerve. We've been able to preserve in approximately 90% of patients over the years, a cumulative patient experience, as far as facial strength, and that's been a fascinating. You don't want to take an acoustic tumor out and then have a patient have a complete facial droop, which used to happen, unfortunately, too often. So complications, and that's just one example, the complications rate has significantly been improved. It enables them to have more aggressive interventions. Instead of really finely kind of digging away at a tumor, they can be a little more aggressive because they have some confidence. Hopefully you've generated enough confidence in the surgeon with what you're doing, but they have some confidence that the signals at least are not changing during the course of the surgery. So they can operate a little bit faster, which also helps with patient outcome because the less time they spend in the OR, the less time they're under anesthesia, the less time they're under mechanical ventilation, all of these things that can cause complications intraoperatively. So it also can conceivably reduce surgical procedure time, although sometimes our setup takes about an hour. So surgeons will sometimes question as to whether it truly saves time, but depending on the length of the procedure, it can conceivably decrease the amount of time, decrease the patient costs, and also I put that way down here, but certainly litigation is another thing that unfortunately we Americans are, at least American physicians, are all too often subjected to. Okay, so we actually had the surgeon cutting away, and these are, again, all of the procedures, and things that I haven't mentioned were deep brain stimulation and other emerging units, and then cortical stimulation mapping, which I'll probably concentrate on in the talk. So this is one of the things that actually really fascinated me during my residency and fellowship, was being able to actually map the brain and its functions. It's actually fantastic because very often the patient will be awake in the OR and we're actually stimulating and interrupting their speech, or we're stimulating and causing their finger to move, or stimulating and unfortunately causing a seizure to occur. But we have everything under control. We have anesthesia has the drugs that they need. They can actually bathe the area with cool saline to actually stop the seizure in its tracks. So it actually is much more safe than one would think. So here I just showed for an example like how this correlates to functional MRI, where we have the left-hand motor area and the left-hand sensory area. It's just indicated here by these red and yellow highlighted areas. But what we're trying to do is find the central sulcus, in this case with our somatosensory evoked potential signal, and we find something called a phase reversal. And it's kind of beyond the scope to explain the details of that, but the motor area would be anterior to the central sulcus, and the somatosensory area would be posterior. So you really can kind of pinpoint where these crucial, quote, eloquent parts of the brain are, so the surgeon does not resect them and cause more morbidity than existed previous to the tumor or the epileptic focus area. Okay, so this just shows that there's actually a paint by numbers thing that is generated within the OR for the surgeon to kind of, they actually do put these sterilized paper numbers on the surface of the brain to actually figure out where the areas are. So this is a fairly complicated one in which the mapping was done quite extensively, both frontally, at the vertex, and then also, kind of in the occipital area, maybe some visual things. You can actually stimulate the brain. Sorry if this is disturbing. I see someone covering their face. Okay. But this is the brain, okay. And so you can actually stimulate the brain, and actually the patient will see flashes of light, so in the occipital area. So it's just really, really fascinating, very exciting work. And then again, what we sometimes will do is we'll actually implant both surface and depth electrodes within the brain where we think the seizure focus might be occurring. Again, so we can actually pinpoint the areas that are the excitable parts of the brain that actually cause seizures. And then based on the mapping, we can decide, is it safe to resect that focus or that area of the brain? We can do things like memory testing, we can do things like speech testing, and then again, now that we have the functional imaging capabilities that we didn't used to, we can actually have kind of complementary sets of information, both intraoperatively and extraoperatively, and really, really pinpoint where both the seizure focus might be, and also if it's safe to actually resect that part of the brain. Very exciting stuff. Since I finished my residency, another great application has come into play in that we actually can stimulate the brain, the deep parts of the brain, for various neurologic diseases. Specifically, the first one that was approved was Parkinson's disease, and that's actually revolutionized Parkinson's disease treatment. What's really, really neat, actually this I'll just explain, this is the microdrive that actually kind of by fractions of a millimeter drives these electrodes deep into the parts of the brain. Specifically the part of the brain that we're going to be stimulating is the subthalamic nucleus. So right here it's shown as STN. And as you're kind of coursing through these various layers of the brain, you'll see different sorts of firing patterns. And what's really, really interesting is when you get to the crucial motor areas, when I passively will flex and extend a part of the body, you'll hear a burst. And you actually see it on the screen. So it's really, really, you can actually find out the areas that are involved with the Parkinson's disease. And then actually, you can have tremor cells that you actually see. And once you actually put your microelectrodes or your macroelectrodes within the area, the subthalamic nucleus, when you turn the device on instantly, either the tremor goes away or it is decreased, or you actually have an improvement of the bradykinesia, which is the slowed movement. So it was instantaneous treatment effects intraoperatively. So you can actually test within the OR exactly, that and pinpoint a really good trajectory for these depth electrodes. So that has just been really, really interesting. I guess I can have, about 10 more minutes? 5 minutes?
We're scheduled to end at 10:30, but if you all are willing to stay, and the professors are willing to.
Okay, all right. So I'll now talk a little bit about some of the research projects I've been involved with. Just a couple of the ones that I think are the most interesting and probably the best fit for this talk. I'm actually collaborating with some of my epilepsy colleagues, Drs. Yobes, Bujarski, and Thadani, as well as this company called Neuropace, which is based in California, who have actually come up with a device, a responsive neurostimulator, that actually can detect and then stop seizures with a counter pulse, electrical pulse within the brain. which is really, again, just from my standpoint, just fascinating. So it's a device that can be used for partial seizures of partial onset, and they can be either just very local or they can have secondarily generalized seizures. Most of our patients who end up being in these sorts of clinical trials have very medication refractory epilepsy. So either they're on 4 or 5 medications, and you can imagine the multiplicative effects of all the side effects of being on these medications, which can sedate them, it can make them cognitively dulled. They're tired all the time, they're nauseated, they're just not feeling very well. And you have a device like this that can conceivably decrease the need for being on those anti-epileptic drugs that actually can respond specifically by a set of parameters for both detection of seizures as well as stimulating the seizures. So it's in this, at this point, fairly complicated to program it, but there are actually simulation algorithms that the company has come up with, and you will apply a different detection and stimulation algorithm, and you can predict whether the patient will be able to respond in a positive way to the seizure triggered stimulation. So the detection is accomplished by electrodes implanted at or near, as far as you can determine, the area of the seizure focus. And the stimulation is delivered at the time of detection and then before the actual seizure spreads. Okay, and so this was actually based on pacemaker technology. The people who actually established this company, NeuroPace, were involved with some of the more advanced pacemakers that we see today, and also an implantable defibrillator. So actually I was talking to some of the engineers there, and they said it's actually kind of interesting because the heart and the brain kind of operate in different sorts of ways. The heart has a regular rate and rhythm, so it's very, very kind of uniform, hopefully rhythm and rate, and it adjusts depending on your physiologic demand. Whereas the brain, when you have a regular rate and rhythm, it's a seizure. So the brain is actually fibrillating in a way, you can kind of think, whereas when the heart fibrillates, it's chaotic, more or less, and it's really something that you don't want. So they actually affectionately call this device the brain fibrillator. So I thought that was an interesting way to look at it, because you're kind of breaking that regular rate and rhythm that then sets up the networks that then spread and cause the actual epileptic seizure. So this is a diagram of hopefully it's visible, and there's an external programming device that you actually put once it's implanted on the surface, and there's a electromagnetic coil that actually will both sample from the device as well as program the device, and it's actually really, really pretty ingenious. And what the patient is given is they're issued a laptop with the wand, so they actually can sample the recordings, and they're actually told to actually sample them as much as possible, and they upload them telephonically to the server at NeuroPace. And NeuroPace plays with the data. Then they come to clinic, and they give us advice as to what are the best ways to adjust their detection and their stimulation parameters. And it's really, the people there are just fantastic. They're very helpful. So they have the implanted leads are there. They have various sensing amps as well as stimulators. And there's a detection logic, as I talked about, in a microprocessor. And via telemetry, you actually can sample the data and get an idea of what's going on. And this is how the device looks. And you can have the electrodes be on the surface of the brain. So there are 4 electrodes, either surface and or depth electrodes, just like I showed with the deep brain stimulator. And it turns out that the depth electrodes can be very useful for seizures of temporal lobe onset. So you can implant these depth electrodes near or at the hippocampi, which often are part of the circuitry with epilepsy. So this is what happens, ideally, not all the time, where you have this stored EEG, okay, and then you can see the seizure kind of brewing. You see how the frequency and the amplitude is kind of increasing, and things are actually entraining here, because as things become in sync, that's actually when the seizure is starting to spread, and you have networks of neurons within the brain that actually synchronize, and that's when you have your tonic-clonic movements, or even just the kind of spacing out episode that the patient might have. So what the device does is it actually is there are various detection algorithms, things like the change in the line length, the change in the frequency, the area under the curve. There are various sort of detection techniques. And it can be actually, you set sort of tolerance limits as far as percentage change for these sorts of detection algorithms. And it can be individualized for the patient, so it won't falsely discharge on a regular basis at least. And so you get the stimulus here, and then suddenly everything is quiescent afterwards. And they actually, they don't have the ability to actually do the Fourier transform online, but they're working on it. But that can also be helpful, at least after the fact. You can determine, yes, this was truly a seizure. This is their typical frequency pattern as far as what happens during their particular seizure.
When you do that stimulation, does the patient freeze, or is there any physical?
Nothing happens, and at least in our experience.
Driving a car, and if that thing just went off.
Yes. And you would think, I mean, certainly this was a double-blinded prospective trial, and I have to say that the device is not approved yet. I do think it will be, but I can't actually guarantee that, nor can NeuroPace. The FDA really is quite the bureaucratic organization. There aren't too many people here from the FDA, but it's necessarily bureaucratic, I guess. We don't want to implant these devices that are dangerous. So, as opposed to a pharmaceutical product, the devices they tend to be a lot more strict about. So it's really taking quite a while to get them to approve it. But they're crunching the data. They're supplying more and more data. We have longitudinal collection of data still occurring, so they're analyzing. But it did reach statistical significance as far as improving the ability of these patients or decreasing their seizures. So that was true. As far as the patient actually detecting it, none of the patients that we have been following, and just by talking to our colleagues at other institutions, no one seems to be detecting it. Initially, maybe patients imagined things, but it wasn't consistent. So it's actually quite fascinating in that you can do this with minimal side effects, and patients tolerate this very well. To my knowledge, none of our patients have wanted them to be explanted. None of them. So, and we followed, I think, 7 patients, something like that, 7 or 8. And we follow them pretty closely. The next thing I just want to quickly talk about, because this is an exciting sort of project that we're dealing with, and actually it's getting a lot of press, not our project per se, but the BrainGate. I think people have heard, probably at least some of you in the audience have heard about BrainGate. That's a brain-computer interface sort of thing where you have, quadriplegic patients who have this device, this wired device that goes through the scalp and the skull, actually connected. And initially they were just surfing or operating a computer and surfing on the web. And then later on, they actually had someone who was actually operating a prosthetic limb. So we actually feel that this is, in a way, suboptimal because you have, yes, an invasive electrocorticogram in these patients over a crucial part of the brain, say the motor area, for instance. It is invasive, and there are actually wires that are going through the scalp and the skull. So it could serve as a nidus for infection. I mean, that can be a problem. So it would be nice if there was something that was a little less invasive, quote, minimally invasive. Everything, unfortunately, in medicine is invasive to a certain extent. So something that's minimally invasive, but also has a high fidelity of physiology signals. So I've been asked by Dr. Scherer and Diamond, who are both here, and then Dr. Roberts is our neurosurgeon involved, to actually get involved in this project for neural probes, microelectrode probes. And this is the scalp showing it's non-invasive, but it has low resolution in diagnostics. So it may be difficult for the resolution of the signal to actually finally control a prosthetic limb or to detect seizures, whatever you're trying to do with the actually invasive probe. So these are the things, this is the armamentarium we have right now. Okay, and these look pretty nasty. It looks like very archaic and invasive. But these are the things that they're actually using for this BrainGate project, in which you actually have kind of a comb-like structure or just a, a 3D array that you're actually sticking into that part of the brain. So it is invasive, plus they're wired, and that creates a problem. So this is something that Dr. Scherer's actually devised, in which we have an optoelectronic silicon probe, which can actually be put on the surface of the brain or within the brain tissue that's on the order of 10 to 100 microns in its largest diameter. So it's really small. So it is minimally invasive. So here you have it. You can hardly see it on a dime here. Okay. And so it actually is powered and sampled both by optical signals transcranially. Okay. It's of course, optical fibers have, that innovation, that engineering innovation has enabled us to do this. And Dr. Diamond, Sol Diamond, actually looked at to see how deep the optodes can reach within the brain, and it actually reaches pretty far down, enough that you could conceivably have a probe on the surface of the brain and be able to power it as well as sample from it. It can do recordings of various types, and I'll talk a little bit about the potential capabilities of this device. But it goes down far enough that certainly you could actually do EEG recordings. There's no question. And there's hope that it could conceivably help one to actually power a prosthetic limb, too, potentially, because you're right over the motor cortex. So you can conceivably implant these. We have not implanted these yet. We just received the Hitchcock Foundation grant to actually start the basically biocompatibility and also testing the ability to signal processing and the powering techniques. We'll be implanting these in various rodent models. So we plan to start this summer. So we just got at least our first pilot grant to actually test this. Okay, so it has photovoltaic power sources on the chip itself. Okay, and you can kind of see how the optical power and the generated current is pretty good. It's actually within the realm of where we need it to actually power the probe. But again, we have to have the optode over the area optimized so that it actually powers the probe, and so it can actually do that. And then we can actually, it has a CMOS chip in which you can actually record things, and this is one of the ways that Dr. Scherer actually tested it. He tested it in rat hearts to see if it could reproduce the ECG signal through the chest wall. And actually, it did quite well as far as reproducing the signal. The actual electrode, the standard EEG electrode versus the CMOS chip there. And he actually was able to sample it transthoraxically, which is perhaps a different sort of level of invasive, whatever, as far as the impedance of the overlying tissue than it would be for a skull. But it's actually means that this was actually, in a way, an initial proof of concept. The other thing that can be implanted on the chip is you can put spectroscopy on it, capabilities, and it can actually detect light of various wavelengths that can give you an idea of oxygenation and deoxygenation status in the brain. And this is something that Sol Diamond is very interested in, is the oxygenation, deoxygenation of the brain and how it correlates to electrical activity in the brain. So-called neurovascular coupling. So you can actually detect various sorts of substances such as air, methanol, IPA at the various, and you can